Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 8th, 2025, and we're looking at an ICLR conference paper published about 3.5 months ago on January 22nd, 2025, titled On Scaling Up 3D Gaussian Splatting Training. This paper presents Grendel, a system that scales up 3D Gaussian splatting, or 3DGS, by distributing the training across multiple graphics processing units, or GPUs. 3DGS creates detailed 3D scenes using many tiny 3D shapes called Gaussians, but complex scenes often exceed what a single GPU, those powerful chips for parallel calculations, can handle. So this first figure really shows what Grendel can do. On the left, we see a reconstruction of the Rubble dataset. It's at 4K resolution and uses a staggering 40 million Gaussians. On the right, there's the Matrix City dataset at 1080p with 24 million Gaussians. Both of these complex scenes were rendered using 16 graphics processing units, showcasing how Grendel handles these huge projects. The paper notes Grendel achieves excellent reconstruction quality, often measured by PSNR. That's peak signal-to-noise ratio, where a higher value means a better, more accurate image. Okay, so this next figure really clarifies how Grendel works differently. Part A shows the traditional 3D Gaussian splatting training pipeline, essentially the whole sequence of training steps, all on one graphics processing unit. Part B then shows Grendel's approach. First, it divides the Gaussians among several graphics processing units. Then, using what's called all-to-all communication, where these units efficiently share data, it splits the rendering task by pixel blocks. It even processes a, quote, batch of images or multiple views simultaneously. This distribution is key to overcoming memory limits. Building on how Grendel distributes the work, this next figure shows us something really interesting about the Gaussians themselves. It plots the cumulative percentage of Gaussians against their size, specifically their quote, Gaussian footprint radius, which is essentially how much screen space a single one of these 3D shapes covers relative to the total image width. We see for different scenes like train, bicycle, and rubble that the vast majority of Gaussians are actually quite small. This characteristic, known as spatial locality, meaning each Gaussian only influences a small local area, is key for Grendel's efficiency, especially for that sparse all-to-all communication we talked about. Alright, so building on that idea of spatial locality, Figure 4 here presents a heat map of the trained dataset. A heat map, in this case, uses colors to show the number of rendered Gaussians per image tile, with redder tiles indicating more Gaussians. You see, detailed regions like the train are red, needing many Gaussians, while simpler areas like the sky are blue. This clearly shows an imbalance in rendering intensity across the image, which is why Grendel uses dynamic load balancing, a way to adjust work distribution. Then, Figure 5 illustrates how each graphics processing unit efficiently considers only those Gaussians whose footprints intersect its assigned pixel area. So, to understand how Grendel handles training with larger batches of images, Figure 6 offers key insights. These three plots examine batch size, the number of images processed together, against properties of the gradients, which are the signals guiding how the model learns. The first plot shows that as batch size grows, gradient sparsity, meaning how many gradients are effectively zero, decreases. The second shows gradient variance, how much these learning signals differ, also drops. Consequently, gradient precision, the inverse of this variance, rises then plateaus. This behavior supports Grendel's batched training and its learning rate scaling. Okay, so this next chart, Figure 8, really drives home the speed benefits. Even for a relatively small scene like train, it shows training speed up. Those are the blue bars, and the peak signal-to-noise ratio, which again measures image quality as the orange line. As we increase the number of graphics processing units and the batch size, for instance, going from one graphics processing unit with a batch size of 1 up to 16 graphics processing units with a batch size of 32, the speed up jumps dramatically, over 5 times faster. And crucially, the image quality stays pretty consistent. So those speedups are quite impressive. In essence, the work on Grendel tackles the major memory and computation hurdles in 3D Gaussian splatting, or 3DGS, which is a technique for creating 3D scenes from 2D images. By distributing the work across multiple graphics processing units and using smart techniques like dynamic load balancing and an optimized atom optimizer, a popular algorithm for adjusting the model's learning process, Grendel enables much larger, higher resolution scenes and significantly faster training. Thanks for tuning in to the AI Research Roundup. I'm Alex, and we'll see you next time.